What I'll be talking about today is a rather old subject, vanadium dioxide. I'll give you a little bit of the history and a somewhat detailed introduction and tell you why it remains to be interesting over many, many decades. Saying that without funding, without money, nothing moves, and I've been rather fortunate to have support of ACRB, Nanomission, DST, and in more recent times, CSIR Bhatnagar Fellowship, which ended earlier this year, and this NRF National Science Chair. These have been generously funding our research. So what I'm going to talk about is vanadium dioxide, but before I talk about vanadium dioxide, I would like to set it into the right context, because early transition metal oxides show this rich phenomenon of metal insulator transition that was discovered very long back in 1959, and I dare say less than 3% of the audience in this hall were even born at that time. So it's really a very, very old subject, and what you see here is conductivity plotted as a function of one over temperature, inverse temperature, and you see that the conductivity has catastrophic changes at some particular temperatures, a first order transition from a very low conducting state to a very highly conducting state, signifying that there's a metal insulator transition. Highly conducting state is, of course, the metal, and the low conducting state with exponential increase in the or decrease in the conductivity as you decrease the temperature is the insulating state, and you have this first order transition in many of them. What we are going to talk about out of this class of compound is vanadium dioxide, which is shown over here, which also you can see there's a first order transition from an insulating state to a highly metallic state. And this is a very well-known thing. It's called the rutile phase, R phase, I'll be referring it to, and there's a monoclinic phase, M1 phase, and you'll see why I put that one, because there are several other monoclinic phases that will be emerging as we talk about the later parts. What do we know about VO2 and what is there to be known? Because 1959 already this was discovered, the metal insulator transition, where you start with vanadium dioxide, increase the temperature, there's a characteristic temperature 340 Kelvin, below which it's an insulator and above which it's a metal. This very simple observation, of course a very interesting observation, kept the condensed matter physicists who are interested in the correlated physics as well as in the context of the metal insulator transition busy for about 6 decades to understand this very transition. But besides, and I'll be touching on that briefly to tell you what is the present understanding of the community to describe this particular phase transition. But what else can you do with vanadium dioxide? Of course, we know there are many different parameters. For example, we have the temperature as a parameter, but we can also change the pressure. And we can have a temperature pressure phase diagram, and you can see that the phase line, this is the one that I have talked about so far, but as you change the pressure, you can have phase transitions and a very rich phase diagram that emerges both structurally as well as electronically. So pressure is an obvious parameter that one can treat. So set pressure aside, and what else then can we do? We can start doping the system. For example, instead of vanadium oxide, at the vanadium site, which is a 4+ ion, I can put chromium, which goes in as 3+ ion. So basically, forget about this, what ionic charges are, but what we are doing is to dope the system with holes, and I can deviate from the integer filling, and I know that has a tremendous consequence for the correlation physics, that at integral filling gives me an insulator, but as I dope, I go into a metallic state, as we know for the high temperature superconductors, colossal magnetoresistance, and almost every other example that we know of. And so chromium doping gives rise to a very rich phase diagram of different structure types as well as different conductivity types. So that is also another thing one can do. What else can you do? We can also look at polymorphism. VO2, this is one particular structure that I talked about, R phase, rutile, and M1 phase. It has other polymorphs, the P of VO2 itself, and they have different kind of properties. One can look at that. So as I walk through, some of these parts, some of these dimensionalities of vanadium dioxide, we'll explore as we go along in this talk. So first, the one that we understand rather well now, the rutile to M1 phase transition that I showed that Morin had discovered way back in 1959. The rutile phase is the unit cell is shown by this dashed line, where the vanadium atoms are arranged along these lines. And they're absolutely equidistant. If we look at this tetragonal butyl phase, you find that vanadium atoms are absolutely equidistant. So if you think of hydrogen atoms arranged exactly equidistant and the correlation physics is not playing a very important role, what you would expect is a half-filled band of this kind, which will be metallic then. So hydrogen atom arranged in a chain and having no other instability or electron-electron interaction will give rise to a half-filled band, which will be metal. But as you lower the temperature, you get into this monoclinic phase, which is the solid line showing you the unit cell, has a very peculiar distortion of the vanadium ions. The way it distorts is that now you can see that it doesn't stay at these corners, but moves up basically, and the next one moves down, making this vanadium distance shorter and the next vanadium distance longer. So this one becomes shorter, that becomes longer, and that alternates everywhere, giving rise to a dimerization of vanadium atoms and a long bond here. And this dimerized state is like arranging hydrogen molecules now. Instead of a chain of hydrogen atoms, you now are arranging hydrogen molecules, and you know that the molecule would be dictated by the strong bonding antibonding splitting of the two hydrogen 1s level interacting with each other, giving a large separation, which is shown over here. And then this weak hopping across the dimers will give rise to some bandwidth which is not sufficient to overcome the band gap, and so it will open up a band gap. And this was an idea that was presented by Goodenough soon after, and he explained the metal to insulator transition as you lower the temperature associated with this structural transition, where equidistant vanadium ions, the chains, make a transition into the dimers. This dimerization physics or Peierls physics takes over, giving rise to the why the metal goes into an insulating state. There was this very little, and I have always been intrigued by this, that Goodenough pointed out not just this half-filled band. He said a little bit of this half-filled band overlaps with this another band of the vanadium d states, leaking out some of the electrons. He didn't make any comment. There was no importance of it, and nobody has talked about it till we started looking at some other system, and I'll come back to this very point later in the talk, but I wanted to draw your attention because I think it is a great intuitive genius of Goodenough that had anticipated that this plays some important role, and that will show up later in this talk. This particular paper that came in 1994, much later after Goodenough, essentially said what Goodenough said, but in a very provocative manner that was like, starting up a hornet's nest in the community of the correlated physics by saying that the VO2 doesn't need correlation to understand. And that really got everybody up in arms. There was extreme amount of debate and controversy and bad blood flowing in the community. But the fact that correlation is important was quite obvious from experimental data. And one of the best ways of looking at the correlation effect is to look at electron spectroscopic data, which essentially, for those of you who don't know what it does, is maps out, let's say, how the electronic states are in the occupied part, or maps out the spectral weight up to the Fermi energy or the chemical potential of the system. And these are very old data. Let me very quickly bring you to more recent data. This is in 2004. You can see when the system is in the metallic state, there's the chemical potential. You have a large intensity spectral weight at there. There's the R phase, the metal phase, signified by the fact that you have fairly sharp Fermi direct cutoff of a continuous spectral weight going across the Fermi energy. And as you lower the temperature in the system, so various temperatures, metallic state is given here. And as you lower the temperature, suddenly at a temperature, it makes this transition. The spectral weight qualitatively changes from this large intensity at the Fermi energy to almost no intensity at the Fermi energy, signifying an insulator. But the point that everybody drew attention to, that besides these states which characterize it as a metal, there's a large weight far down away from the chemical potential which mimics the insulating spectral weight, and that must come from correlation effect, even for the metallic state. And that's true because if you were to try and explain these states from the band structure calculation that PRL claimed in 1994 is enough to understand, you would find that it cannot understand at all, because that kind of density functional theory with no correlation effect will describe the spectral weight to look like this. This cutoff is essentially coming because of Fermi Dirac cutoff of the occupied part, but this large amount of intensity that is lying outside the DFT calculation predictions is coming because of correlation, drives the spectral weight out of the single particle description and throws it over a much larger, wider energy range, and that you can see. So correlation plays a very important role. Of course, the 1994 paper didn't make it as clear as also the fact that this M1 phase, if you do a true, honest density functional calculation as well as you can, in the approximations that were available at that time, one didn't get an insulating state. One got a very small overlapping metallic state with a sort of a small negative band gap, as it is sometimes called, basically almost like a semi-metal. So it didn't drive it all the way to the metal insulating state. Finally, the resolution came, and there's the final word, I would say, where dynamical DMFT calculations were done, the dynamical Mill field theory, where you take into account correlation better than the standard DFT calculations. And they found that, yes, indeed, in the monoclinic state, you get this gapped state. There's a chemical potential, a clear gap forms, whereas in rutile phase, where you have this dashed line, you have a metallic state with a high density of states or high spectral weight at the Fermi energy. Describing the system that it's neither Peierls physics is enough nor Mott physics is enough. We need both, either correlation assisted Peierls or Peierls assisted Mott physics is what describes the R to M1 phase transition. A few other characteristic of it that I would like you to remember, because for the part of the talk that I'm going to talk about later, is that if you look at the core level spectroscopy, so basically what you're doing is creating a very deep level core vanadium 2p electron, which has nothing to do with the valence electron. If you pull it out and look at its energy distribution, since you have created a hole in the vanadium side, a very localized hole, it tends to pull electrons towards it if it would be a metallic system. But if it is not a metallic system, it cannot rearrange the valence electrons so easily. So this screening effect would show up in a metallic state, but not in an insulating state. And you can see that the insulator has a very clean spectral feature, nice and sharp, one single peak, but the metal has this huge broadening, and this broadening, this part comes from the fact that this core hole is attracting the metallic electrons to come closer to it to screen itself out. So the screening electron, signature of the screening electron is a very good signature of the metallic state that you are talking about in the rutile phase. And there's a very clear distinction between the insulator and the metal in the case to R and M1 transition. Another very clear expression of experimental expression is the optical conductivity, where at high temperature metallic state, you have this Drude type behavior. And at low temperature, you have the clear gap formation in the system. So you can see that as you go from high temperature metallic state, you have the Drude peak, and then at the low temperature, you have a clear gap signature. I would like you to remember that also. And now that we know R to M1 phase transition, I would like to switch over, trying to understand some polymorphic axis of VO2 to explore another one. There's a very famous one, the polymorphism. So I'm now going to travel across this. There are two different polymorphs of VO2 known, B phase and A phase. I'll not be talking about A phase today, but I'll be talking about the B phase. So the B phase is sitting somewhere, and we are going to look at a phase transition that happens. It's contributed by a very large number of people, color-coded for the kind of contributions they have. It is Venke's group that created the sample. It's very difficult to make this sample. The red people helped us in the synchrotron activity. The blue, the pink ones are mainly theoretical inputs. It's driven by Bernabé Paul. He was a PhD student. Now he's a senior scientist at Max Planck in Halle in Stuart's group. So the phase transition, you can see it very clearly here. So what I'm showing you is resistivity as a function of temperature. This is a standard R to M1 phase transition that I talked about. The metallic state and the insulating state, a very large transport or conductivity, many orders of magnitude change in the conductivity. The B phase has a more distributed but even more intense, a more larger order of magnitude change in the resistivity. And one is trying to understand this B phase high temperature and the B phase low temperature, what the differences are. And when you start to look at it and carefully compare it with the R to M1 phase, you begin to understand that it's qualitatively different. Remember the R phase, where we have every vanadium atoms are equidistant and beautifully arranged in a vertical 180 degrees arrangement, linearly like this. Whereas the M1 phase, as I told you, has a dimerization and a slight zigzag also that I had not emphasized, but it has a slight zigzag, but it dimerized vanadium. If you look at the B phase, the low temperature phase, where you expect the dimerization, indeed there's dimerization. And the dimers in this representation, you don't see it very well. These golden vanadium atoms are dimer paired, but the other vanadiums are not dimerized. So basically half of the vanadium sites are dimerized, the remaining half are not dimerized. And that's very important. But what is even more surprising, you go from the low temperature to the high temperature phase, the structure, the space group does not change. You continue to have half of the vanadium still dimerized and the other half not. All that changes is the extent of dimerization and extent of the tilt that I talked about just now. The tilt increases or decreases and dimerization increases or decreases, but the structure type remains exactly the same. I'll not go into that, but to summarize the rather surprising aspects of this B phase transition that you're looking at, the space group remains the same, C2 by M, which is a very rare thing, that you have a first order phase transition connecting two phases that have the same space group, same structure. And the other aspect that I have already talked about is half of the vanadium atoms are dimerized, the other half not, which implies that I cannot even think of extrapolating what I understand of R to M1 phase transition, where the dimerization of all vanadium atoms are essential to understand the metal insulator transition, to understand the physics that I'm seeing in the B phase. B phase is a qualitatively different beast. And how do we try to understand that? So we started looking at it with spectroscopy, and I'll contrast the spectroscopic results for you to appreciate the drastic difference, qualitative difference between the two cases. This is the standard R to M1, our own data. This is the metallic rutile phase, high spectral weight at the Fermi energy. This is the insulator, a very large shift, a very strong dip. But this cutoff, as I've been telling you, is because of the Fermi Dirac statistics. I don't have any electrons above, so I can't see them. But there's a way to see that. I can divide this spectrum by the Fermi Dirac statistics and anticipate what it was like beyond. And if I do that, you can see this is the rutile phase spectral weight as it would have gone across the chemical potential, and this is the insulating M1 phase. There's a drastic loss of spectral weight as I go from the metal to the insulator, as one would expect, of course. If I now compare that with the high temperature and low temperature B phase, the shift is very small. The change here is much smaller than here. And if I do the same exercise, I find that as if this high temperature phase, which is the highly conducting one, is also trying to form a gap at the chemical potential, which looks qualitatively different from what I see over here. In fact, the difference becomes even more acute when I start to probe the ability of these valence electrons that are giving me the transport property of high conductivity, how well it can screen. Remember, in the M1 rutile phase, it screens very well and there's a screening signature. But if I look at there's the metallic screening, but if I look at the high temperature and low temperature phases, there's hardly any change at all, which would say that I don't have any screening electrons available for the high temperature phase, though it has a very high transport conductivity, which is drastically different, and there's hardly any difference between the low temperature and the high temperature phase. Even worse is when you look at the optical conductivity. This is to remind you what the rutile metallic state looked like and what the M1 phase, rutile-like peak and a clean gap in the insulating phase. And there I'm now going to put this B phase at various temperatures. This is the one that is in the low temperature phase, which is supposed to be the insulator. This has, if at all, a gap, if I extrapolate the data, a gap of a very small size, but there's hardly any change if I change the temperature, as if something is getting filled up, but it's not a coherent state that is building up here to give rise to a Drude peak. There is no Drude peak in this highly conducting state, and it seems that a gap-like feature underlies whatever is the electronic distribution or description of this system that has to be. The understanding of this comes from the DMFT calculation that I told you Jan and Zilke did. What I'm showing you here, let me explain in a moment, that of course you know exactly the structure. I call them low temperature structure LT, high temperature structure HT, simply because they have the same crystal structure, so I cannot designate R and M1. But I know the lattice parameters, I know the atomic position, so I can do a realistic calculation for the low temperature as well as for the high temperature. And that's what I'm going to do. But DMFT can be done for different temperatures. So I can do the calculation for different temperatures, including the electron excitations and what it does to the electronic structure. Of course, if you take any insulator and do a finite temperature calculation, no insulator is insulated at finite temperature, simply because there's this very boring thermal excitation of electrons across the gap. So there is certain number of free electrons and holes available, there's some conductivity, and that fills up the gap, it becomes non-zero. So we like to know what happens at zero temperature to be able to define whether the system is insulating or metallic. Now that we can do by theory, but unfortunately I cannot take the high temperature phase and lower the temperature and see what the high temperature does, because there's a crystallographic transition where the lattice parameters, everything changes via the first order transition. So I'm going to ask the question, what happens to the high temperature phase if I could take it to zero temperature? What happens to the low temperature the state that I can take it to zero temperature? When I do that, I find, and here the purple would be high temperature and green the low temperature, both of them turned out to be gaps. So the high temperature phase is actually an insulator. The low temperature is an insulator, there's no controversy about that. I start to increase the temperature, keeping the same structure. When I increase the temperature of the low temperature phase, I see the gap survives, and because of thermal excitation, there's a filling of the gap. At this temperature, this gap still survives in the high temperature phase, but the filling is a lot more rapid. And then when I heat it up a little more, you can see that there's qualitative change in the high temperature phase, as if the underlying electronic structure has changed so drastically that it's not a thermal effect that we are seeing in the case of the low temperature case, where the gap feature always survives. So there is a non-trivial change thermally induced for the high temperature phase to give rise to this. What does it? What is the change that comes about? The change that comes about, here we are just plotting the weight of this spectral weight exactly at the chemical potential at various temperatures for the low temperature phase, which is essentially thermally driven. So you have a sort of a monitor, a reference point, thermally how much I expect it to change, and the B high temperature phase non-trivially changing with respect to thermally excitation. What I'll now tell you is what I had introduced earlier, and I'll show you that our theory shows that actually as we are changing the temperature, this intra-dimer transfer from this sigma to the pi bond, from the A1G orbital to the other orbitals, changes drastically. And I'll show you more quantitatively in a few slides later. And as it happens, that means that the underlying electronic structure itself is changing drastically, completely changing the scenario as the temperature is induced because of this intra-dimer transfer of electrons within the dimer from one kind of orbital to another kind of orbital, giving it rather incoherent but large intensity spectral weight at the chemical potential. How can I probe that experimentally? It turns out that one can probe this polarization of this level as it gets depolarized by transferring more and more electron. There's a particular signature in X-ray absorption linear dichroism it's called. It's technical, let's not go into that. It's basically whatever I have extracted here. If the system is very polarized, I'll see large intensity here. If the system is less polarized, I'll see low intensity here. And you can see that this becomes much smaller at the high temperature phase. At low temperature, it's much more polarized. Exactly the way that you have anticipated. Low temperature remains polarized. You have a sigma band that's almost completely filled with hardly any leaking out into other orbitals. But at high temperature, a large part of this sigma bond hands over the dimer, the level, hands over electrons to the other state. And this can be seen that there's a direct correlation between the optical conductivity. If you look at the M1 state, which has very clean gap, and the various B states, and the R state, which has a large Drude peak and a finite energy that we are looking at. And that correlates exactly oppositely with the M1, which is highly polarized. This particular feature is very strong, and that polarization keeps decreasing as we go to the metallic state, exactly reversing that trend. And this can be quantified if you think of just a dimer and ask the question, what is this dimer going to do? And that dimer, of course, can have a local and a non-local singlet. And if I'm in the limit of non-correlated, these two components would be completely identical weight. Alpha 1 will be equal to alpha 2. In the limit where the correlation or Coulomb interaction strength is infinitely large or much larger than the hopping strength, this alpha 2 will approach 0, so I'll be left with an alpha 1, which will be 1 by square root 2. Now that allows you to define essentially a parameter. This is the Heitler-London singlet state, totally non-local singlet state, which is a sort of a measure for us of correlation effect. And this particular parameter then changes from the completely this delocalized or non-interacting scenario, it will be equal to 0. And in this scenario where it is only the non-local singlet, local singlet has gone to infinite energy and so has no limit, it will vary to 1. And now I can start to plot the few R, M1 and B phase, low temperature and high temperature in different parts. You can see this is the color coding. That means M1 state, as I heat it up from this temperature to high temperature, this is the temperature axis, you can see that the non-local singlet dominates the physics completely. But if I take the high temperature phase at low temperature, which it would have shown me a clean gap, as I increase the temperature, very clearly the non-local singlet is also giving way to the local singlet, as if the U is becoming effectively small. Why does it happen? And that is explained by this axis, which is measuring essentially how much is the orbital, the dimer state occupied. If the dimer state is only occupied and nothing else, I would have a number of 2. You can see that the M1 state has a very large dimer occupancy and the other orbitals are very little populated. So are these, but this one, as I heat up and goes to the high temperature, a huge amount, the difference from this number 1.6 to 2.4 electrons are moving out of the dimer bonding state into the other states, and that's what gives rise to this drastic change and change in transport property that I have talked about. And so entire physics is related to leaking out of this electrons into those. Having said that, so basically a very quick summary of this particular part, that this low temperature phase is just a bad insulator in the sense that it's a small band gap insulator, but it's a insulator as we understand it. But this high temperature phase is actually a worse insulator. It is an insulator that aspires to be a metal and mimics to be a metal, but actually is an insulator and has confused us for a very long time, mimicking and claiming itself to be a metal to insulator transition, whereas what we have been looking at is an insulator to insulator transition. Now that I have talked about polymorphism, let me walk you through 2 other examples in the next 10 minutes, 5 minutes each, because there are many, many things one can talk about in this. So as I promised, the chromium concentration. In the chromium concentration, of course, many things can be done. I'll just look at one particular case. In a lower chromium composition, higher chromium composition is some other physics. Low chromium composition, you can see there's a new phase that comes in, T phase. And that goes into this M2 phase, which is different from the M1 phase, and I'll tell you what the difference is. And that, when you heat it up, goes to the R phase. And so you have a structural transition and an electronic transition. It's a very rich physics. I'll focus only on the structural transition and try to understand that, because there were some controversies. And I'll tell you what the controversy is. This already tells you that you anticipate 2 transitions. This is essentially differential scanning calorimetry that tells you whenever you see a bump, there's a phase transition. There's a clear phase transition. This is from the R phase, high temperature, temperature increasing. High temperature R metallic phase goes into the M2 phase. That M2 phase goes into the T phase, this small bump. So M2 to T transition. So there are 2 transitions. The question is, this is the first order transition we know. What is the order of this transition? And this is where the claim was, okay, let me tell you the difference between T and M2 phase before I tell you what the claim was. It's rather interesting. In the T phase, all chains, again, we have identified chain, but there are 2 kinds of chain, green chain and blue chain. All the chains have dimerization. This is short, that is long, and this is short, that is long. Now the chains have, it's written here, you can see that these 2, in chain 1, the dimerization is of about 0.3 angstrom, the difference between this short bond and long bond. But in chain 2, dimerization is much stronger, is 0.7 angstrom. So very strong dimerization, weak dimerization. But this zigzag, which is also written down, you can see this zigzag is much stronger, deviation from 180 degrees is much higher, and this goes to 180 degrees, so weaker zigzag. So weak dimerization, strong zigzag, strong dimerization, weak zigzag. You go into the M2 phase, now they fall apart. What do I mean? Chain 1 has only the zigzag and no dimerization. and chain 2 has only the dimerization, no zigzag. So it's a very beautiful structural evolution that we find in this case. And what's the consequence of that? I'll come to in a moment. These are the R2M1 phase that I have already talked about. And this is an old report that had claimed that, look, by measuring those bumps that I talked about in differential scaling calorimetry data, I can get the enthalpy, and the enthalpy for these two, chromium concentration of 0.5, chromium concentration of 3, and they extrapolated this, saying this is the region where I have first order transition, and beyond that, presumably I have a second order transition. The question is, what is the order parameter that I should look at? Now, when you start to look at, for example, if you look at the volume across the R to M2 phase transition at 5% doping here, where the second order is claimed, this is the T to P transition. R to M2 transition, there's a huge change of volume. Wonderful, I can recognize a first order transition very, very clearly. But if I look the volume change across the M2 to T phase, the volume seems to change absolutely continuously, doesn't indicate that there's a first order transition. And this is the reason why people believe that slightly higher concentration of chromium that I'm showing over here gives rise to second order phase transition. But this is where my student Shayak looked at it rather carefully, and he said, let's look at the dimerization and tilt from the crystallographic data. We know that chain 1, if I'm looking at only the tilt, and the tilt is now defined as the long bond minus the short bond. So there's the tilt measure, there's the dimerization measure, and there's the tilt measure, which is measured by 180 degree minus the deviation from the 180 degrees. You can see that the dimerization of chain 1 vanishes at the T2 M2 phase transition, but the dimerization of chain 2 vanishes only M2 to R transition. Whereas the tilt, if I look at, the tilt of the same chain 1 now survives up to beyond this T2 M2 transition, goes away only M2 to R transition, and the reverse happened for chain 2. It still goes away T2 M2. So there seems to be a correlation that T2 M2 transition is indicated by the dimerization of chain 1 and tilt of chain 2. And the M2 to R phase transition is signified by the dimerization of the chain 2 and tilt of chain 1. So he said that
we've passed half an hour, so a couple.
Yeah, exactly. So he combined the two and then figured out that the order parameter that you really need is this kind, which combines the opposite ones. And then the question is, what is the order? And if you look at this order parameter and try to fit it, you can see that it's actually a first order in all the cases, all the compositions, and that's what he extends. So you have an all the way first order transition in this case. So I'll just spend next 3 to 4 minutes to be in time to talk about one. So summary I have just now said, so I'll not spend that time. So what is the other axis that we should like to look at? There are many pressure I'll not be talking about today, but I want to talk about this. This is a very unusual transition. You see that there is R phase, goes to R phase from metallic state to a semiconducting state. That itself is not so much surprising, but the fact is that I'm doping charge carrier into the system as I go from here. As I dope charge carrier, the system should go more metallic. And there's the expectation even in this paper, a very famous review of modern physics, that at integer filling, you of course have this Mott-Hubbard at a particular U value, you get the insulating state. But you have a cone or some kind of a distribution. If you go away from the integer filling, you get into the metallic state. The clean part is the metallic state very quickly. Here it seems that I'm doping the system, I get into an insulating state. I start with a metal, dope it with holes, and get into an insulating state. What is going on? And this we are going to again look at the valence band, and we'll extract two parts. You remember this is the signature of the metal. There's the chemical potential, large weight tells me metal. And this is the higher binding energy peak, which is the signature of correlation-driven state that are thrown out. So the intensity of this, if it relative to this increases, that means correlation effect is becoming more stronger. As I dope the system, I expect this to go down and this to go up, but exactly opposite happens, as you can see. As I'm doping more, 3%, 5%, 6.5, and 8%, my correlation induced effect is going up, and I can quantify it, and you can see that correlation effect is growing. The incoherent peak, the large weight in the higher binding energy peak. And similarly, I can also look at the core level. I told you the core level, the screening peak, remember, The screening peak measures how the screening channel's ability is. I can quantify that by some spectral fitting. You don't have to worry about that. But basically, I'm going to look at this bump, how it changes. If the metallicity decreases, or if it increases, this should increase. Otherwise, it should decrease. And here you can see that starting as I increase the doping, this fellow keeps becoming smaller and smaller. I can quantify that again. So everything is saying correlation effect is increasing as I'm doping the system, which is completely counterintuitive. And I'll just sum up the story in the last 1 minute that is left of the 35 minutes, that the correlation effect essentially is increasing because of a structural reason. If you look at the structure, C by A ratio in the system actually is constantly increasing when you're doping the chromium, which essentially decreases T, making U by T increase as you go along this direction. But what happens to the doping? That's a red herring in this problem. Why? Chromium 3 plus dopes holes, but exactly the same number of vanadium 4 plus sitting around captures those holes, converting themselves to vanadium 5 plus, leaving the rest of it exactly like VO2 as it was. So it is exactly VO2 physics, and we have enough spectroscopic signature to prove that chromium 3 plus exact same number gets captured by vanadium 4 plus to convert itself to vanadium 5 plus. So you're left with a vanadium VO2 vanadium 4 plus C with some disorder. So disorder also impacts the ability to remain metallic, but the correlation in fact increases, giving rise to this change. So let me summarize with the permission of the chair that I have talked about this R to M1 transition that we have understood already about 20 years ago. We talked about the composition driven, and that we are in the process of understanding. Hopefully within the next 1 month, everybody will understand when it gets published as a temperature driven what the phase transition is. I talked about this particular transition, the structural aspects. There are many other interesting aspects, pressure, that I didn't talk about. We have a paper if you're interested in the pressure variation, so I did not talk about it. I didn't talk about the other temperature driven MIT, which you have looked at, this transition as well as this transition. But I did talk about this very unusual transition going across. And I did not talk about there's a very unusual transition, structural transition going from M2 to what we call M4 phase, a very, very peculiar thing where different experimental probes don't agree with each other. And that story will be told another day. Let me end thanking you for your attention. Thank you very much.
Yeah, a few questions.
Thank you, Professor Sharma, for a very nice talk.
Thank you.
How easy or difficult is to prepare VO2?
VO2, there are VO2s and VO2s. So the R phase, rutile to M1 transition that it shows is relatively easy to make. It's not very difficult. And you can also make single crystal of it by various methods. The B phase is very difficult to make. In fact, the B phase that we looked at that Venki made was made as a thin film on a substrate, making use of the substrate strain to stabilize the B phase. So that's a lot more difficult. But the other chromium doped, aluminum doped that I talked about are as easy as to make VO2, the R phase. Okay? That you can do by arc melting, essentially.
Well, I guess the fields that you have measured out using X-rays, right? How confident are you about that?
About that.
The field angles.
Those I am reasonably, the structural data is we're rather convinced of. Most of the structural data that I showed you are derived from single crystal analysis.
I just saw your paper.
Yeah.
But,
The aluminum doped, we had a single crystal, and so we could analyze that very, very clearly. And that's the one. And then you do Rietveld analysis of the powder diffraction also.
the neutron would have given a better
the neutron would give. VO2 itself, much of this has been done. So there's not enough any controversy of the structure. Except for the M2 to M4 that I talked about, that I did not talk about. There are some very peculiar thing, and their different probes don't agree with each other. But rest of it, the structural aspect is understood.
local structure there.
Yes. And that's something that we are in the process of understanding right now. XFs and the XRD are completely, they contradict each other. And we love that contradiction.
Yeah, it's a well-known the oxygen content, which is very sensitive to the phases and then the properties. Particularly when you have a doped system. So because it's our experience, for example, we have also stabilized what you have stabilized in thin film under pressure. And
Under pressure, it can be done.
under
Yeah.
pressure, but including oxygen, more oxygen, which means stoichiometry. So if there is an oxygen deficiency, then you end up with M2 phase or M1 phase. So it's very crucial to get the triclinic and the M2 and then the rhomboidal phase.
Absolutely.
Yeah.
No, that we fully appreciate as experimentalists. That's something that we worry about a lot, and we even actually try to determine the oxygen content. You can take the VO2, burn it all the way to VO5, and then with a large amount of sample, you can estimate. Because you cannot do any of the titration methods because, I mean, you and I can go on talking about experimental lists O's, but that you can do separately.
Rajiv, one question.
Yeah, so I have maybe it sounds like a very naive question.
Those are the
Myself.
most difficult ones.
Yeah, so the thing is that, of course, this is the correlation physics is very important, but I'm not following this field. But is there any magnetism present in this system?
Absolutely. The magnetism is used as a standard thing. R2M1, because all the vanadiums dimerize, so the susceptibility just drops off. So you get a polysusceptibility at the high temperature deuterial phase where there is some moments, and the dimer is a singlet. And so you get a first order transition into a totally different magnetic state. And so we are using magnetic probe to understand that. So it's done quite extensively.
Okay, I think we should close because there are.
Yeah, just one moment. Is it, what's the value of the ordered moment there?
I should look it up. If you look at it's in the order of the vanadium 4 plus what you'd expect, not very different, but the exact number. And it all, as an experimentalist to experimentalist, I can get you a number within a ballpark that you want because susceptibility fitting, chi0 is available to you. There are, what range you fit, all these have an impact. So I don't give a fixed number, but it's not anomalous to what one would expect to vanadium 4 plus.
I think we should thank Didi.
Thanks a lot.